Good morning, everyone, and thank you for being here. We're really excited today to kick off a brand new series, Computer Hardware, Architecture, Components, and Modern Systems.
Sounds fascinating.
Indeed. And our first deep dive is into the foundational concepts of computer architecture. The essential stuff underneath everything.
A blueprint, basically.
Exactly. Our mission today is to look past, well, the shiny screens and the easy interfaces we all use. We want to get right down to the fundamental blueprint that governs how computers actually work.
Deconstruct it to its core.
Precisely. Reveal that elegant logic behind digital computation. We hope this gives you, our listener, a bit of a shortcut to being really well informed on core architecture. We'll hit some surprising facts, some key insights, all crucial for digital literacy today.
Okay, so what's the roadmap?
We'll cover the von Neumann architecture, then the functional hardware components, get into binary logic, the ones and zeros, and wrap up with a quick tour through computing history.
Excellent. Where should we start?
Let's begin with the absolute foundation. Could you break down the three key principles of the von Neumann architecture, the ones that really set the stage for the stored program computer?
Absolutely. And it's amazing how influential this design from the mid-1940s still is. You got John von Neumann at the EDVIC project.
Back before that, it was all physical rewiring, like ENIAC.
Exactly.
Yeah.
Imagine taking days just to change the task a machine did. Von Neumann's big idea was treating the program, the instructions, just like data, stored in memory. That changed everything.
And it's still the basis for pretty much every device now.
Yeah.
Smartphones, supercomputers.
Pretty much all of them. Understanding it is key. So the first principle, single, unified memory. This is maybe the most critical part.
Okay.
Think of it like this. Both the program instructions, the recipe, and the data, the ingredients, live together in the same main memory space.
Okay. Not separate areas.
Nope, all mixed together. This makes programs incredibly flexible. You can load them, change them, manipulate them easily without touching the hardware. It basically enabled software as we think of it.
Got it. Principle one, unified memory. What's number two?
Number two is the central processing unit, the CPU. This is the engine, the brain of the operation.
Right.
It has two main parts inside. First, the arithmetic logic unit, or ALU. That's where all the math happens, addition, subtraction, multiplication, but also the logical comparisons like A and D or not XOR.
So not just number crunching, but decision making too.
Fundamentally, yes. These logical operations are the basis of all commands. Then right inside the CPU, you have processor registers.
Registers, those are like super fast little storage spots.
Exactly like that. Tiny, extremely fast memory right on the chip. Like a chef having ingredients right on the countertop for immediate use. They hold the data the ALU is working on right now, or maybe the address of the very next instruction.
Makes sense. Fast access is crucial there. And the third principle.
The third is the control unit. This is the conductor of the orchestra, maybe the traffic cop.
Okay. Directing the flow.
Precisely. Its job is to manage the whole process. It does this through a continuous cycle. The fetch, decode, execute cycle.
Fetch, decode, execute.
Yeah. It fetches the next instruction from that unified memory. Then it decodes, it figures out what needs doing, and finally it executes it by telling the ALU, the registers, and other parts what to do.
And this cycle just repeats incredibly fast.
Billions of times per second in modern processors. It's what brings software to life.
That really lays it out clearly. Unified memory, CPU with ALU and registers, and the control unit running the fetch, decode, execute cycle.
That's the core of von Neumann.
But as with many great designs, there's a catch, isn't there? A limitation. Can you explain the von Neumann bottleneck?
Ah, yes, the famous bottleneck. It's a really important concept because it stems directly from that first principle, the unity memory.
How so?
Well, because instructions and data share the same memory space, they also have to share the same single pathway, the bus to get to and from the CPU.
Only one road for both things.
Exactly. They can't both travel at the same time. You can either fetch an instruction or you can fetch data, but not simultaneously.
I see. So the CPU, which is super fast,
ends up waiting. It's like having an expert chef who can chop and cook at lightning speed, but they only have one narrow path to a single pantry to get both the recipe book and the ingredients, one item per trip.
The chef spends a lot of time walking back and forth, waiting.
Precisely. That's the effect, a traffic jam. The CPU is idling, waiting for the slower main memory to deliver the next thing it needs. This seriously limits the overall speed of the system.
And overcoming this bottleneck is a big goal in computer design.
A huge goal. Things like cache memory, which we might get into, are specifically designed to try and alleviate this exact problem. It shows how fundamental that bottleneck is.
That pantry analogy really helps visualize it. Okay, let's shift gears slightly. Thinking about the physical pieces, all computer hardware fits into 5 functional categories. What's the role of the first one? Input devices. And maybe give some examples.
Sure, input devices are basically the computer senses. Their job is to get data from the outside world into the computer.
Bridging the physical and digital.
Got it. They translate things we do, or things happening in the environment, into digital signals the computer understands.
Like keyboards and mice.
Definitely. Those are classic human interface devices. Keyboards for text, mice for pointing, touchscreens, microphones for voice, webcams for video, game controllers. Lots of ways for us to directly interact.
But it's not just us talking to the computer, right?
No, absolutely not. There are also data capture devices. Think about scanners turning documents into digital files, or barcode readers in stores.
Or scientific instruments.
Exactly. Thermometers, pressure sensors, accelerometers in your phone,
Yeah.
all sorts of sensors feeding real-world data directly into computer systems for analysis or control.
Okay, that covers getting information in. Now, for processing devices, the next category. We've talked about the CPU, but there's also the GPU. How do their roles differ?
CPU versus GPU. That's a really important distinction, especially nowadays. The CPU, the central processing unit, is the main brain, the generalist.
The one doing most of the heavy lifting for the operating system and apps.
Right. It has the ALU and control unit designed for versatility, handling all sorts of tasks, often one after the other, very quickly. It manages the whole show.
And the GPU, graphics processing unit.
The GPU is different. It's a specialist. It was originally designed for, well, graphics. Rendering complex images, like in video games, requires doing many simple calculations at the same time.
Parallel processing.
Massive parallel processing. GPUs have thousands of simpler cores designed to do this kind of work simultaneously. But what's really interesting is how their job has grown.
Oh, beyond just making things look pretty.
Way beyond. That same parallel processing power turns out to be fantastic for other things, like complex scientific simulations, modeling weather patterns, or drug discovery.
And AI, I hear.
Absolutely critical for AI.
Yeah.
Training those huge neural networks involves enormous amounts of parallel computation, and GPUs are perfectly suited for it. So yeah, the GPU started with graphics, but now it's a crucial coprocessor for specific, highly parallel tasks working alongside the generalist CPU.
Fascinating how its role has evolved. Okay, let's talk memory and storage. People often mix these up. Can you differentiate primary storage, like RAM, from secondary storage, like an SSD, especially thinking about volatility and their roles?
Good question. They are very different beasts. Primary storage, and we mainly mean RAM, random access memory here, is the computer's short-term workspace.
Where active programs and data live.
Exactly. It's very fast, which the CPU needs, but it's volatile. Meaning, when you turn the power off, everything in RAM disappears. Poof, gone. Its role is to hold the operating system, the applications you're currently running, and the data they're actively working with, all for quick CPU access. Good RAM is essential for multitasking smoothly.
And you mentioned cache earlier. Is that primary storage too?
Yes, cache memory is a type of primary storage, but it's even faster and smaller than RAM and located right on the CPU chip itself.
To fight that von Neumann bottleneck again.
Precisely. It stores the most frequently used data and instructions. So the CPU checks the cache first. If the data is there, great, super fast access. If not, then it goes out to the slower main RAM. It's like keeping your most used tools right on your workbench.
Got it. Super fast, volatile workspace. So what about secondary storage?
Secondary storage is the long-term warehouse. Think SSDs, solid-state drives, or older HDDs, hard disk drives. This is non-volatile.
Data stays even when the power is off.
Correct. This is where you permanently store your files, your applications, the operating system itself. It's your digital filing cabinet.
And the difference between an HDD and an SSD?
Big difference in how they work. HDDs use spinning magnetic disks, like tiny record players, with mechanical arms moving back and forth to read and write data. They offer huge capacities relatively cheaply, but those moving parts make them slower and more fragile.
Right.
SSDs, on the other hand, use flash memory chips. No moving parts at all. This makes them significantly faster, much more durable, quieter, and use less power.
But they tend to cost more per gigabyte.
Generally, yes, although the gap is closing. Other examples of secondary storage would be things like USB flash drives or, going back a bit, optical disks like CDs and DVDs.
Okay, that clears up the volatile versus non-volatile storage distinction. So After processing and storing, how does the computer share the results? What's the role of output devices?
Output devices are how the computer communicates back to us or to other systems. They take the processed digital information, the zeros and ones, and translate it into a form we can understand or that another machine can use.
The opposite of input devices, basically.
Exactly. Giving the computer its voice or actions. We usually think of human interpretable output first. Things like your monitor or display, showing images and text, speakers or headphones playing sound, or a printer creating a physical copy.
Makes sense.
But there's also machine interpretable output. This is output meant for other devices. For example, your network card sending data packets out onto the internet, or maybe a signal sent to control a robot arm, telling it exactly where to move.
So output isn't just for humans.
Not at all. It's any way the computer sends processed information out.
Right. Now, let's zoom out again to the whole physical setup. Could you explain the difference between the system unit and its peripherals?
Sure. This helps organize the physical parts. The system unit is the main box, the chassis, and everything inside it.
The core components.
Yes. The motherboard, the CPU plugged into it, the RAM sticks, internal drives like your SSD or HDD, the power supply that runs everything, any expansion card slotted in. That's all part of the system unit. It's the heart and brain.
Okay. The main case and its contents, what are peripherals then?
Peripherals are all the other devices that connect to the system unit, usually on the outside.
Like the things we plug in.
Exactly. Via USB, HDMI, Wi-Fi, Bluetooth, whatever. They add functionality. Think of the system unit as the star performer, and the peripherals are its essential entourage.
Entourage, I like that.
Yeah, they provide the input and output we just talked about, your keyboard, mouse, monitor, printer, speakers. External hard drives also count as peripherals, falling into that external storage category. They support the main system.
That distinction makes sense. And inside that crucial system unit, you mentioned the motherboard. What exactly does it do?
The motherboard is absolutely central. You could call it the computer's central nervous system. It's the main printed circuit board, the big board you see when you open the case.
Okay.
Its job is multifaceted. It physically holds the CPU in its socket, provides slots for RAM modules, and has connectors for storage drives and expansion cards like graphics cards.
So it connects everything physically.
Physically, yes. But even more importantly, it provides the electrical pathways, the buses that let all those components communicate with each other.
Ah, the communication highway.
Precisely. Without the motherboard and its buses, the CPU couldn't talk to the RAM couldn't get data from the SSD, the graphics card wouldn't get instructions, nothing would work together. It's the backbone holding and connecting everything.
Truly the foundation inside the box. Okay, let's shift now to the absolute lowest level. How do computers actually represent information? What's the fundamental language?
Right down at the bottom, computers don't understand words or pictures or even numbers like we do. They use a system that's incredibly simple but powerful, binary.
Ones and zeros.
Just ones and zeros. It's a two-state system. A 0 usually represents an off state or low electrical voltage, and a 1 represents an on state or high voltage. Every single piece of information in a computer is ultimately broken down into combinations of these two states.
And each 0 or 1 is AV.
A bit. That's short for binary digit. Just one bit doesn't tell you much, so they're grouped together. The most common grouping is 8 bits, which forms a byte.
Okay, 8 bits in a byte.
Yep. And with 8 bits, you have 2 to the power of 8, which is 256 possible combinations. That's enough to represent, say, a single character of text or a specific color value for a pixel.
How do they represent text then? Like the letters I'm typing?
Through encoding schemes. You might have heard of ASCII or the more modern and much larger Unicode. These are standards that assign a unique binary number, represented by 1 or more bytes, to every letter, digit, symbol, punctuation mark, even emojis used in languages all over the world. So hello becomes a specific sequence of bytes representing HELLO.
Everything boils down to those ones and zeros.
Everything.
So if it's all just ones and zeros, how does a computer actually do anything? How does it perform calculations?
This is where the hardware gets really clever at a microscopic level. The calculations are done using millions, or nowadays billions, of tiny electronic switches called transistors.
Billions on a single chip.
Billions. These transistors are the fundamental building blocks. They're arranged into circuits called logic gates.
Logic gates.
Yes, a logic gate is a very simple circuit. It takes 1 or more binary inputs, zeros or ones, A1s, and produces a single binary output, a 0 or 1, based on a specific logical rule. These rules come from Boolean algebra.
Can you give an example?
Sure. The simplest might be a not A. It just inverts the input. If you feed it a 1, it outputs a 0. If you feed it a 0, it outputs a 1.
Okay.
Or an AND gate. It needs 2 inputs. It only outputs a 1 if both input A and input B are 1. Otherwise, it outputs 0.
And an OR gate?
An OR gate also takes 2 inputs. It outputs a 1 if input A or input B, or both, are 1. It only outputs 0 if both inputs are 0.
Simple rules.
Very simple rules. But by combining these gates, A and D, or not E, and a few others like NAND, not AE, and XOR, exclusive OR, in incredibly complex ways, engineers can build circuits that do addition, subtraction, comparison, data storage, like flip-flops, anything needed for computation.
So all the complex stuff we see, 3D graphics, spreadsheets, AI, it's all just a massive number of these super simple gate operations happening incredibly fast.
That's essentially it. Billions of simple decisions per second, orchestrated by the control unit, manipulating those fundamental zeros and ones. It's quite amazing when you think about the scale.
It really is.
Yeah.
Now let's take a quick look back. What was the single biggest breakthrough that moved computing beyond those huge, unreliable vacuum tubes we talked about earlier?
That's easy. The transistor.
Yeah.
Invented in 1947 at Bell Labs. It was revolutionary.
Why was it such a big deal?
Because it did the same job as a vacuum tube, acting as an electronic switch or amplifier. But it was tiny, solid, much faster, way more reliable, and used vastly less power and produced much less heat.
So it solved all the major problems of vacuum tubes.
Pretty much all of them. Before the transistor, computers like ENIAC were room-sized behemoths, incredibly expensive, and prone to constant breakdowns because the tubes burned out. The transistor made smaller, faster, more reliable, and eventually affordable computers possible. It opened the door to commercial viability.
A pivotal moment. What came next? What allowed us to cram so many transistors onto tiny chips and led to things like Moore's Law?
The next giant leap was the integrated circuit, or IC, also known as the microchip, invented around 1958.
Integrated, meaning putting multiple components together.
Exactly. Instead of wiring individual transistors together by hand, which was slow and error-prone, the IC allowed engineers to fabricate thousands and later millions and billions of transistors and the connections between them all at once on a single small piece of silicon.
That must have changed manufacturing completely.
Completely. It enabled mass production. And this ability to shrink transistors and pack more and more onto a chip led Gordon Moore, co-founder of Intel, to make his famous observation in 1965.
Moore's Law.
Right. He noticed the number of transistors on a chip seemed to be roughly doubling every couple of years while the cost was coming down. This trend held true for decades and became a self-fulfilling prophecy driving the industry.
Exponential growth in computing power.
Incredible exponential growth. This relentless shrinking and integration led directly to the microprocessor in the early 1970s, putting the entire CPU onto a single chip, like the Intel 4004.
And that paved the way for
personal computers. Suddenly, you didn't need a university or a huge corporation to own a computer. Companies like Apple and IBM brought computing to desktops and homes. It democratized computing power and, combined with the later rise of the internet, really created the digital world we live in today, from room-sized calculators to the devices in our pockets.
It's an incredible journey driven by those key inventions.
Absolutely. So if we just summarize the key takeaways, it all starts with that foundational von Neumann architecture, unified memory, CPU, control unit, still the blueprint today. Then you have the 5 hardware functions: input, processing, memory, storage, output. Underneath it all is binary logic bits, bytes, manipulated by logic gates built from transistors. And the whole modern era was kicked off by those huge historical shifts: the transistor replacing the vacuum tube, and the integrated circuit enabling Moore's Law and the microprocessor.
That covers the core concepts really well.
Yeah, and understanding these, it's the essential foundation. It helps you make sense of pretty much any digital device you use and where technology might go next.
A fantastic overview. It really highlights how these seemingly abstract concepts dictate so much of our daily interaction with technology. It's fascinating stuff.
It really is.
And if you, our listener, enjoyed getting this foundational understanding, this core blueprint, then you'll definitely want to join us for our next deep dive. We'll be zooming in on the central processing unit, CPU, the brain of the system.
Taking a closer look at that crucial processing component we discussed today.
Exactly. We'll get right into the details of how the CPU works. So thank you all for joining us on this journey today.
Thanks, everyone.
And please don't forget to subscribe to our channel, Tech AI and Beyond. That way you'll stay informed and can continue your deep dive into the truly fascinating world of technology with us.